Nathaniel. My call sign's W2NAF, and I am the founder and leader of the Ham Radio Science Citizen Investigation, or HamSCI. And so today I'll be talking to you about measuring the ionosphere with amateur radio. I'm also an assistant professor of physics and engineering at the University of Scranton, and I've been a ham for quite some time now. So it's really, ham radio. So Boy Scouts led me to ham radio, and ham radio is what led me to my career. So my entire career came about because I was a ham radio operator first, and I continue to do that today. So we'll talk a little bit about some of my more exotic ham radio operating, and that was a couple years ago. It's now, wow, it's been back in 2014 already. I was down at McMurdo Station in Antarctica, which is down here, and I had the opportunity to operate KC4USV, and I was calling CQ on CW. I'm really not a very good CW operator, but I do like it, and so I try to get on once in a while. And but I called CQ, and this is what I heard. And so just listen to this. Did you hear all of that pitch variation, that frequency variation in there? Yeah, so that's not normally what you hear on CW. That's something you hear usually when you're thinking about operating Aurora type of mode, that fluttering. And what you had happening here is that I believe that's exactly what was happening. We had signals coming in from out here, and we were located here inside of the auroral zone. And so the signals must have been passing through, and you could, and when the aurora is active, it's changing. You're getting electron precipitation and all sorts of things happening in the ionosphere that can change the refraction point of the signals coming in, and that can change whether how long the propagation path is, and that translates into Doppler shift. So that's what you're hearing here. So it was that sort of thing that really emphasizes the connection that we have between what we do with ham radio and with space physics. And so between this and around the same time, I also had a chance to go off to Adak Island and help build a super darn radar out there. And I met my friend Ethan Miller, K8GU, and I learned about the reverse speaking network. And I learned that, I saw the reverse speaking network. I'm like, oh, wow, I bet you could really, look at the data that they're collecting and do some science. And so that and also as at Virginia Tech, I met some people who were planning on studying the ionospheric effects of the 2017 solar eclipse. Those two things really led me to start the Ham Radio Sciences Investigation. And so we're a group. We call ourselves a collective because we're not technically, we're not technically a nonprofit organization. We don't have any real standing that way. But we're a group or a collective that allows university researchers to collaborate with the amateur radio community in scientific investigations. And so we want to advance scientific research through understanding through amateur radio activities. We want to encourage the development of new technologies to support this research. And we want to provide educational opportunities for the amateur radio community and the general public. And I think one thing that's really neat about this particular group is it really is a two-way street. It's not just the scientists telling the hams what to do. It's not just the hams telling the scientists what to do. It really is a sharing of information. And a lot of the people in the group actually are, they're like me. They're both scientists and hams. And so we do this for fun, and we do it for our job. And then you get people who are, both, more on one side than the other. But it's really a great group. So what are some of the science goals that we're after? We really have a very broad mission. Broadly, we're interested in any scientific question of interest to the amateur radio community or to the field of space physics. And so examples can include solar flares, geomagnetic and ionospheric storms, traveling ionospheric disturbances, short time, small spatial scale ionospheric variability, connections with the lower atmosphere, and others. Really, this program is very much driven by the interests of the people in it. So if you were to participate in HamSCI and you had a particular interest, we might help. You could come to us and tell us what you're doing. You could ask for suggestions, but you have the chance to kind of drive your own investigation if you want. At the same time, if you wanted to latch on to something we're already doing, one of our interests, that's great too. So a little review of some of the science, how all of this is put together. I realize some of this may be old hat for some of you. For others, it's a good refresher. Maybe some people haven't really thought about this a whole lot before. So I'll just go through it. So first thing we have the ionosphere. So the ionosphere is an electrically charged layer of the upper atmosphere. And that electrical charge, it comes mostly from ultraviolet and X-ray energy from the sun hitting the neutral atmosphere and stripping the electrons off of the neutral particles. So then you have a gas that has both free-floating electrons, free-floating positive protons, and ions, and then you still do have some neutrals mixed in there as well. And so that's the ionosphere. Now during the day, it's more structured. So we call things by different layer names. Closest to the Earth, you have the D layer at around 80 kilometers altitude. Next up, you have the E layer at about 110 kilometers altitude. This is also the altitude where the aurora, the green aurora, typically occurs at. Then you have the F1 layer, which is around 200 kilometers altitude, and the F2 layer around 300 kilometers altitude. And these are all very, rough numbers. Things can vary depending on space weather conditions and time of the solar cycle and where you are on Earth. There's a number of factors, but this is a very rough cartoon to give you an idea. And then at night, when the sun goes away, the free moving electrons, they can find the positive ions again, recombine and become neutrals. And so the ionosphere becomes less dense. But it doesn't go away completely. You still do have an ionosphere at night. It's just less dense, not quite as strong during the day. And at night, you can say that, okay, the D and the E region the D region kind of goes away, and you just get the E region down here. And then the F1 and the F2 region, they combine, and you get the F region up here. Now, why do we care so much about this? That's because this ionosphere is really what enables our long distance high frequency amateur radio communications. And how does that happen? So I'll pause this for a minute. So if you have a transmitter in one location, say this one on this figure, it's in Florida, it's sending out a radio signal, and those signals will go up to the ionosphere, and gradients in the electron density will cause the signals to bend back to Earth. And that's how you can go over the horizon and back to Earth and talk long distances without requiring satellites. And you can actually get multiple hops. So the red one shows a single hop, but if you look behind it, you see these white rays. You can actually see multiple hops. You can go farther all the way around the Earth. Now this movie here, this shows that if you keep the frequency constant, but you change the background electron density, you can see how things change. Basically, the stronger the electron density, the more refraction you're going to get. So the more bending you're going to get. So this movie takes place during the 2017 total solar eclipse. And what you'll see is this is a simulation, a simulated ionosphere. That those are the colors in the background, and then this is a 14 megahertz signal that's being ray traced to go from Florida to Wisconsin. So whenever the computer predicts that the two stations can communicate with each other, you'll see a red line. When it predicts they can't communicate with each other, you'll see the line goes away. So I'll just go ahead and play this. Now soon the eclipse will come on, and the ionosphere becomes weaker, and you can see you get less bending and things escape into space and communications breaks down. And so this is the solar eclipse case, but it's really very similar to day and night. So, during the day, stronger ionosphere, you can support the 14 megahertz band will be more supported. At night, the 14 megahertz band would shut down and the rays escape. So that's holding the frequency constant, but changing the electron density. Conversely, you can keep the electron density constant, but you change the frequency. And that's what we're showing here. So both of these ray traces have the same background ionosphere in place. But here, this is a 15 megahertz signal. It's actually a ray trace of a radar signal. But 15 megahertz is kind of close to 20 meters, 14 megahertz. And then here's a 10 megahertz signal, 30 meters. So you can see the higher you go in frequency, the less bending you get. The lower you go in frequency, the more bending or more refraction. So you can see here, to go 1,500 kilometers, it takes about 1 hop at 15 megahertz for this particular ionosphere. For 10 megahertz, you go 2 hops. So there's more refraction down here. So you can see how the ionospheric state affects the propagation. Now, what's neat is if you are listening to any of these signals, and if you're able to keep track of what signals you can hear and where they're from on a large scale, you can start to see patterns in the propagation, and you can really see how the ionosphere affects things. And what's great is the ham radio community has come up with these systems: the reverse speaking network, weak signal propagation reporter, net, WhisperNet, and PSK reporter, that are able to monitor the communications we as hams make on HF on a global scale in real time and archive all that information. And we now have over a whole solar cycle's worth of observations here. And if you talk to any of the operators of these networks, they'll be more than happy to give you the data. So RBN and Whisper, you can just go and download it right off their website. And PSK Reporter, you have to send Phil Gladstone an email, but they're all very helpful, and we're more than happy to give you this data. And so I started working with these people and used some of their data, and I started looking at things like solar flare impacts. So this is from one paper I did where I looked at a solar flare back in 2017 on September 6th. This is the 15-minute period before the X-class solar flare happened. This is the 15-minute period after the X-class solar flare happened. And this is combined WhisperNet and PSK reporter data. It's color-coded by frequency. And so you can see up here in the 15 minutes before the flare, you had 12,824 communication paths, and that dropped down to 2,293 communication paths for the 15 minutes after the solar flare. So that's an 82% drop in the observed RBN and WhisperNet communication paths, just all of a sudden. And so it's a very dramatic drop. You can see from here that the majority of the drop off occurs over the day side, because that's the part that's going to be most exposed to the solar flare. Here we can see it a little bit easier. So this is a measurement from the NOAA GOES spacecraft measuring the X-ray flux. So this is how you actually measure how much X-ray energy is coming from the solar flare. And so you can see there's actually 2 flares here. There's one at this time around 9 Universal Time or 9 Zulu, and then there's one around noon. And they're both X-class flares. This one's a little bit bigger than that one. And here is the response of Europe on 7 megahertz. So this is a map of all the radio spots, actually the halfway points between the transmitters and receivers over Europe. And then this is a time series of these same spots. So this is showing from 6 to 18 UTC or 6 to 18 Zulu time. And then here you can see this is distance between transmitter and receiver. So you can see on 7 megahertz for most of the time, the typical distance of communications is about 500 kilometers. Right at the first flare, boom, everything gets wiped out. you get a recovery here, and then you get the second flare, boom, everything gets wiped out for an even longer period of time, almost 2 hours before you start to see the recovery. Now, the reason, do you know the reason you get these sorts of drop-offs when you have solar flares? You know that? So what happens is you get a sunburst of X-ray energy, and that X-ray energy gets all the way down to the D region ionosphere, and the D region becomes enhanced. You get more ionization there. And the problem with the D region is it's so close to Earth that there's still a lot more neutral particles than much higher. And so it's actually very likely that an electron will collide with a neutral particle before it can re-radiate the radio energy that it's trying to refract from Earth. And so when it collides with that neutral after getting the radio energy, the neutral particle will absorb that electron's energy and it won't radiate. And so they call that collisional absorption. And so that's what's happening during the solar flare. So you see that here. And then here's what happened in the United States. So the United States was actually at dawn. This dashed line over here, this is the sun line. So when it's highest in the sky, that is noon. And here you can see the United States was first in darkness over here, and then here's dawn, and then you get up to noon around here. So the United States is pretty much shielded from these particular flares. You barely see any effect over here during the first one. And the dawn side, you do see some effect. So you do see a drop off, but this is also the same time that you're getting the transition from nighttime type of propagation on 40 meters going into daytime propagation. So it's really neat how you can see this is all in WhisperNet and RBN data. So what else can we see in these WhisperNet, PSK, RBN observations? Well, when I was one thing that you can see are these things called traveling ionospheric disturbances. And these are waves in the ionosphere, in the ionospheric electron densities. And they're often associated with atmospheric gravity waves in the neutral atmosphere. And these things can cause fading or QSB on HF, and with periodicities of say 15 minutes to a few hours. So if you're on HF and you hear a station or you're working a station and they're nice and strong, but then they fade out and they go away for like 15 minutes to a half hour and then they come back in later, that might be one of these traveling ionospheric disturbances. So again, here's another movie here showing an ionospheric model. This is at 250 kilometers altitude, and you can see a medium scale traveling ionospheric disturbance propagating from the north down towards the equator. And I have a radar field of view positioned over this. And if you look at this one beam of the radar, you can see this this vertical profile of the model. And here you see the waves going through. Now, what's neat about this, again, this is a 14 megahertz ray trace here. So it's very similar to the 20-meter band. What's neat is you can see that the convex and the concave structures on the bottom of these traveling ionospheric disturbances are causing these rays to focus and then defocus as the wave moves overhead. And where the rays get focused together, that's where you get the strong signals. And where the waves get defocused, that's where you get the weak signals. Or another way you can think about it is that sometimes you're able to communicate out at farther distances. Sometimes you're able to communicate to closer in distances, and that changes, oscillates as these wave structures move overhead. So again, we can see this in the RBN, WhisperNet, and PSK reporter data. So I took that same data from, I took data from all three of those networks for 14 megahertz, and I looked at November 3rd, 2017. Here's a 12-hour period from 12 to 24 universal time, coordinated universal time. And here again, you can see this is the distance between transmitter and receiver, and the colors you see represent the number of radio spots transmissions that are occurring at that particular distance versus time. And so if you look at the bottom here, you can see an oscillation moving through the RBN PSK WhisperNet data. And so that's that minimum skip distance moving in and out with time. And so if I looked at that a little bit more closely and I compared it with what we call GPS total electron content data. So we've got the ham radio data on top, and then the data on the bottom here. These are observations made by ground-based GPS and global navigation satellite system receivers throughout the United States. If you have a GPS receiver on the ground, more expensive receivers can actually receive the GPS signal on two frequencies. Usually, like the ones at 1500 megahertz and other ones I think at 1100 or 1200 megahertz. But depending on how many electrons are in the ionosphere, that will delay one of those signals coming to Earth more than the other. And you can back out the total number of electrons between the receiver on the ground and the GPS satellite in space by looking at the delay between those two signals. So that's what they're plotting here. And wherever you see red colors, that means you see higher ionospheric densities. Wherever you see blue colors, that's lower than average electron densities. And if I play this movie again, what you'll notice is that where the skip distance is closer in, you're going to see more red colors. And where the skip distance is further out, you're going to see more blue colors. That's because the red corresponds with higher electron densities, so you're going to get more refraction closer in communications. The blues correspond with less electron densities. That's going to allow less refraction, allow the communications distance to be longer. So let me play this again. So you should see a red phase now. Then we're coming into the blue phase. So you can see this is a really large coherent wave structure moving through the ionosphere overhead of the entire continental United States. There's the red, the closer in propagation again. And we should come out to another blue phase. And this is changing with a periodicity of about 2.5 hours. It's really neat watching these maps. You can really see lots of very interesting wave structures. You may notice that these dots actually move. They kind of creep along, move in time. That's because the ground receivers are tracking moving satellites overhead. So the location of the data point actually moves with time. So where does this particular thing come from? For this particular event, auroral activity is actually the likely cause. We were able to use ground magnetometer data from the auroral zone from something called the SuperMag network, and we could see enhancements in the auroral electrojet occurring about 2 to 3 hours before we start seeing the traveling ionospheric disturbances here. And similarly, at that same time, we could use an incoherent scatter radar in Poker Flat, Alaska. You can see enhancements in the electron densities at that time. So charged particles from space streaming into the upper atmosphere. That's what we're seeing here. And that's causing Joule heating in the ionosphere, and then also in the, which heats up the neutral atmosphere as well, launches these waves that can then propagate down into the mid-latitude region. And you can look at the timing of this, and it does, the timing of this would go back to about where these observations were. So this was a really nice thing that we can really see these sorts of waves, disturbances in the amateur radio data set. And I was just able to publish this particular result in the AGU, American Geophysical Union, journal Geophysical Research Letters. So that was just published this week, actually. So these traveling ionospheric disturbances, that's really a driving question for my particular interests with HamSCI right now. And that's led to a couple of recent grants. We have one from NASA, and this is a 2-year grant called Enabling Space Weather Research with Global Scale Amateur Radio Data Sets. And the purpose of this one is to develop some empirical models of the TIDs, the traveling ionospheric disturbances we see in the amateur radio data, and use that to both develop a model that might give you some predictability and it of when these types of disturbances are most likely to occur, and also to try and again understand what's driving these disturbances, what's the main cause. And then I also have a NSF career grant that's a 5-year grant. And this one is, again, to look at traveling ionospheric disturbances in the amateur radio data, but also to do more modeling and a little bit more theoretical work with it. So that's driving a lot of the work. And with the NASA grants, actually a little bit more collaborative. So I'm working with Bill Engelke, AB4EJ, down at the University of Alabama, and Phil Erickson, W1PJE, up at the MIT Haystack Observatory. So that's the work I've been doing with the WhisperNet PSK reporter, things like that. But those systems really weren't designed for ionospheric science. So we also have a HamSCI project where we're trying to develop new instrumentation to make more precise measurements of the ionosphere that are still of interest to amateur radio operators, and the equipment would be affordable to amateur radio operators. And so the idea here is we have all these wonderful software-defined radios these days that are tremendously capable. So we would be designing a new one of those that would have some additional features specifically to help us with the science that would let us get radio signals from, say, 100 kilohertz up to 60 megahertz. And we could take that data and we can process it in all sorts of different ways to look at ionosons of opportunity, to look at Doppler shifts from standard stations. Again, we can still monitor the amateur radio modes. We might be able to do some lightning detection and HF noise characterization. We'd also have a GNSS or GPS receiver on here that would serve a couple of purposes. One, it would act as a GPS disciplined oscillator to allow for precision frequency stability and frequency measurement. Also, it would provide precision time stamping. And then some of the more advanced models would have the ability to monitor total electron content the way I showed before with that map. We'd also have a ground magnetometer, which could measure changes in currents flowing overhead in the ionosphere. And if you're familiar, this is a very important index for, or I shouldn't say index, this is a very important measurement for doing space physics studies, but it's also very important to amateur radio as well. I'm sure you're all familiar with the KP index. KP is derived all using ground magnetometer measurements. We, of course, have a local computer to crunch all of this data and be able to show it to the local user. We are going to have a VLF, very low frequency receiver, on here now too, that my friend Jonathan KC3EEY is developing. And this can all go to the internet and then to a public database. And this is a highly collaborative project. We have, University of Scranton I'm the lead investigator. We've got, again, University of Alabama, Bill Engelke, working on the software for this. We have a very close relationship with Tapper on this project. In fact, it was from working with Tapper that this whole personal space weather station project basically got put together. They're the ones that are designing the new software-defined radio, which they call the Tangerine SDR, and they're developing the magnetometer board as well. Case Western Reserve University is developing a low-cost version of the personal space weather station, which is focused just on measuring Doppler shifts from WWV and WWVH. New Jersey Institute of Technology is doing the ground magnetometer science, and MIT Haystack, Phil Erickson, the science collaborator. And then, of course, in addition to all of this, we have these weekly telecons for on Monday nights for the Tangerine SDR, on Thursday mornings for the Personal Space Weather Station. We just get volunteers from the amateur radio community who are interested in, participating in this. And so we'll just get all sorts of people come onto our telecons, and they will purchase equipment. They'll set it up at their house. They'll contribute data. They'll give us input, help us with the engineering, give ideas. So we just have a lot of great support from the amateur radio community as a whole. And we're very grateful to support from the National Science Foundation and ARDC for supporting, providing financial support to the project. So some of the instruments, as I said, we have a low-cost version, which we call the GRAPE Personal Space Weather Station. We do already have a GRAPE version 1 that you can build yourself. And this is focused as a fairly low cost target. It's focused entirely on monitoring the Doppler shifts of a signal from WWV. So WWV in Colorado is a frequency standard station. And so if you listen to 10 megahertz, it should be rock solid on 10 megahertz. But if you're somewhere that's not right next to WWV, if you're somewhere farther away and your signal is going through the ionosphere, you'll find that the received signal carrier is not exactly at 10 megahertz. It varies quite a bit. And that's because as the ionosphere moves up and down and changes, the path length changes, and it puts Doppler shifts on the signal. You can't measure this with a conventional off-the-shelf ham radio without, because the local oscillator is just too unstable. So the radio itself will have more variation than the ionosphere does. But if you use a GPS discipline oscillator to frequency lock your receiver, then you can start to make these measurements. And so the GRAPE uses one of these GPS disciplined oscillators to make those sorts of measurements. Now, this is not taken with a GRAPE, but this was taken during the eclipse, and it's using the same sort of technique. It's just a really nice illustration of this. This is during the eclipse. This is listening to WWV on 10 megahertz at WA9VNJ station near Milwaukee. And you see in the morning, you see these positive Doppler shifts as the ionosphere is building up and the path lengths are getting shorter. The eclipse comes on. You see these negative Doppler shifts as the ionosphere goes away. You see positive Doppler shifts as the eclipse goes away and the ionosphere builds up again, and then negative Doppler shifts in the evening. So you see it very clearly here. This is interesting right here. This little spike in the middle, that's actually a C-class solar flare. So even C-class solar flares can have an effect on radio propagation. Over here, this is, we also have the Tangerine SDR, and this is going to be an FPGA-based software-defined radio. Now, the main difference between what we're doing with the Tangerine and what we're doing with like a standard Kiwi that you can buy off the shelf right now is the Tangerine, we're really designing it to pay extra attention to the precision, timing, and frequency requirements needed for science, as well as provide multiple phase-locked coherent receive channels that would let you measure polarization of the incoming signal and things like that. You can get similar specifications right now from an EDIS USRP, but to do that would cost you around $3,000. So our cost target for this is $500 to $1,000. This is being totally designed by Tapper. I should say we're in a little bit of a tight spot with this at the moment due to the global chip shortage. We have the whole thing designed, but we can't get the FPGAs we need, and that's been a real drag. Fortunately, we do have a number of FPGA development boards that have the FPGA we want on there. So we're going to continue doing development with that at the moment. But let's all hope that this chip shortage gets better. If you have a radio like this, you can start doing things like listening to ionosons of opportunity and making these oblique ionograms. And this is a movie made by Dev Joshi, who was my postdoc over the last year and a half. So this is a measurement taken at my house using Inetis USRP, listening to an oblique ionosonde in down in Virginia, and you can see how things really change with time. So it's a very nice result. So when the Tangerine gets built, the intention is to port this sort of observation onto the Tangerine. And then here's our ground magnetometer. Again, we have a number of these prototypes that are actively being run. They're actively being used right now. I have one in my backyard. Jules Maddie, K2KGJ, has been doing a lot of engineering work, volunteer work on this, has a number of them running at his house in New York. And so this has a 10 nanotesla target field resolution. This is orders of magnitude better than what's in your than the magnetometers in your cell phone. And it's a 3-axis. So that's neat. We're hoping to have these for sale in the Tapper store within the next few months. Again, we're trying to get chip shortages getting us here as well, but I think we are finding the chips we need for that. So hopefully we'll be able to get those built. This is more examples of the eclipse. I already showed you this. This is an example data from an actual grape that is where you can see some traveling ionospheric disturbances. So ultimately, when we're starting to collect all this grape data and try to look at traveling ionospheric disturbances in the network as a whole. So another really neat project that's been asked is, okay, we can see we can do all this really neat science with just the carrier of WWV, but you can also, we also asked what information besides just like the time of flight and frequency measurements can we get from WWV? So we have a team of people that are developing a custom waveform that can be broadcast on WWV. And we're actually, at least as of last week, I think it's still going on right now, WWV and WWVH has been transmitting this specially encoded signal that our team has designed on minute 8 and minute 48. And we've been receiving that, and people on our team have been starting to look at that. But if you go to hamsci.org/WWV, you can learn more about it. You can see some nice animations, and you can listen to the signal as well, and you can learn more about that. So if you want to join HamSCI, how do you do that? HamSCI now has over 500 members. And what do we define as a member? Basically, a member is anyone who joins our listserv. And that's the very basic criteria for membership. You join by visiting hamsci.org. There's a nice big blue button here. You can click that. The main Google group is open for discussion for all things related to HamSCI, so you can jump on there. You can ask questions. You can just listen. We also have a number of specialized email lists. So if you're just interested in the grape, we have an email list for that. If you're just interested in helping with the Tangerine SDR, we have an email list for that. And we have telecons on Zoom every week that you can join as well. If you get involved up on top, it will tell you, you will get the links to the Zoom telecons. We have 3 main telecons every Monday night, 9 p.m. Eastern. We have one dedicated to the Tangerine SDR. This one's technically run by Tapper, and this is primarily engineering telecon to support Tangerine SDR and magnetometer board development. Thursday mornings at 10 a.m. Eastern, Case Western runs a telecon to support the Grape Personal Space Weather Station, and we have both engineering and science discussions on there. And every other Thursday, including tomorrow at 3 p.m. Eastern, during the academic year, we have a more general HamSCI telecon, and this is a science-focused telecon open to all HamSCI topics. So tomorrow we're going to be seeing what people have about relating to the Tonga volcano event, which had a rather big impact on the ionosphere. And then our big event of the year is coming up March 18th and 19th. And if we are still open for in-person registration, if you can make it to Huntsville, Alabama, this is going to be a really great event. It's going to be at the U.S. Space and Rocket Center, 2-day event, March 18th and 19th. And it's going to be hybrid, in-person and virtual. So you can either come in person or you can just go on Zoom. We'll have talks, posters, and demonstrations. There will be a special event station. You can go to hamsci.org/hamsci2022 and you can get the whole schedule. We have 3 invited speakers. We have Dr. Tamitha Skov, who I'm sure many of you are very well aware of, the space weather woman. She'll be talking about space weather impacts in the ionosphere, and she will be there in person. Mr. Jim Bacon, G3YLA, he's a British meteorologist and sporadic E researcher. He'll be talking about sporadic E. He'll likely be virtual. And Dr. Chen Peng Yang, he wrote the book Probing the Sky with Radio Waves, which is all about how the field of ionospheric physics was developed, and amateur radio plays a very large part in that. You've gotten your QSTs this past December. You've read about the 100th anniversary of the transatlantic tests. He writes in great detail about all of that. So he'll also be virtual this year, but we have at least 1 in-person guest speaker and then 2 virtual. It'll be really wonderful to have all of them participate. So that's pretty much it for the formal part of this presentation. I'm grateful to all of the people who've provided, financial support, time, our volunteers in the amateur radio community, people who've developed all of this open source software that lets us do our analysis. So as I said, this concludes the formal part of this. I'll be happy to answer any questions you have about the HamSCI workshop or the program or anything else related to what we're doing. So thank you.
Well, thank you. And I've just taken Spotlight. Can you lower your desktop and we'll see what we got here for hands and people who've got questions.
I see Oscar's hand is up.
Can you lower your desktop?
Me?
Yes,
Sure.
please. There you go. Thank you. Oscar, take it away.
Yeah, wonderful presentation, really quite interesting. I do have a question now that you may have some monitoring station that you can control. What about monitoring the ionosphere as well with active regions that you have earthquakes and see how it reacts as well? I know it's embedded within the space weather as well, but monitor, like, for example, we have in Puerto Rico quite active area during the last couple of years. That will be something interesting to follow up how the ionosphere behaves.
Yeah, I think that's a great question. So after an earthquake occurs, you can get that can launch different waves on the surface of the Earth that can then couple with the neutral atmosphere and then reach up to the ionosphere, and you will see those as traveling ionospheric disturbances as well. So I know you can see that in GPS to electron content, and it's likely we'll be able to see it in GRAPE data as well, but you'd have to go looking for it. So it's certainly a possibility. I do want to say that, so it's definitely a possibility.
Add the earthquake monitor as well into your radio, SDR radio as well. So that would actually see it locally, because if not, you have to make a cross section of time and the activity that is recorded.
You do need to be really careful with this. So there absolutely is legitimate peer-reviewed literature out there that shows the effects of earthquakes on the ionosphere. But one thing you do have to be careful of is if you're going to, you have to look very carefully for those signals, and you really have to do a good job making sure that it's actually the earthquake you're seeing and not some other space weather event or some other sort of thing. So what you have to be careful of is you can't just say, every blip you see is caused by the earthquake or something like that. And I know that there's some danger of people doing that. So you have to be very, very careful with that. But if you do a careful analysis and you do things properly, I think it is possible to see some signatures in there. But it's still a developing field. There's still a lot of work that needs to be done with that.
Thank you.
All right, are there any more questions out there, folks? Great presentation. Really appreciate you coming on and doing this.
Thank you. And I really do encourage, if anyone can make it down to the HamSCI workshop, we'd love to have a few more people show up. We've got a really great program going. So please consider doing that if you can.
Okay, this presentation will be posted on YouTube and a couple other social media areas. And so there's a good, where we get most of our viewing. Was the time we used to get 500 or more people on this present. And later on, as people started realizing they can just watch the video, and we're seeing a lot of that.
Yeah, that makes sense.
Yeah. Okay, I don't see any more hands up. How you doing, Barry?
Nothing at all in the chat.
Wow. Okay, this is going to be we'll wrap this one up short tonight. Again, really appreciate you coming in. He had his little scare. We weren't able to get a hold of you, and they were, oh geez, is he going to make it? But he
No,
did.
I'm sorry. Like I thought I said I know I said I was going to do it, and then I saw the email. I got an email yesterday from you asking me to fill out the Google form, and I couldn't get around to it until tonight. It's just been so busy, but
That's okay. I went to your QRZ page and I got a lot of information from there, so that helped a lot.
yeah.
Yeah, when do we get done tonight, can you send me your slides, your PDF slides, so I can put,
Yeah, I think I emailed them to you before the
Already
meeting.
there on the email.
Yeah, they're already there.
okay.
And
There's
I
a
do
question
see
in chat, Dan.
Okay, take it away, Barry.
Frank WB8YHD asks, do you see this technology growing into a tool that hams can use in real time?
I certainly hope so. I mean, that's certainly one of the goals for the personal space weather station. And I'd like to see that. It'd be great to see that with the even with the traveling ionospheric disturbances, the way we plot that WhisperNet PSK reporter data. Yeah, if we could use that in real time, that would be kind of neat. And maybe even the way I've been plotting some of that data, so you can see those traveling ionospheric disturbances. Maybe I can work with some of the website operators eventually to show some of those things in real time. Yeah.
Okay. Is there anything else out there, Barry?
Nope, that's all.
Well,
There is definitely so much to learn.
oh yeah. Oh yeah.
And me too. You know, every time I go learn more stuff, I'm like, oh my gosh, there's some more stuff I need to learn.
Suck it in while you can. You get a little older, it gets a little harder to shove it in there.
Yeah. Oscar has another question.
I would really love to have your SDR radio and all these sensors to install it at the university. That would be lovely to put it at the roof of the university. So probably I'm going to get in contact with you by the end of the week and try to get one of those.
That'd be great. Yeah, the one that we have available right now is the Grape version 1, and that's something you'd have to build at the moment. But we have instructions for that on our website. If you go to, I can put that in the chat here. Make sure I get the right one. hamsci.org/grape1.
And believe me, we don't have any problem building kits and developing electronics as well. So,
well, that should, if you go to that website that I just put in the chat there, that should point you in the right direction.
Okay. Appreciate that. The chat will be forwarded out to everybody too, and I send out the follow up with the links to the video.
Great.
Well, okay. Unless somebody's got some more here. Anybody got any comments out there? Yes. Okay, well, I think we'll wrap this up tonight. Again, appreciate it very much. We'll get this posted out there and you'll get a copy of all that also. that, so anyway, thank you again for everybody that attended. We got another one of these tomorrow. And for those that are going to attend us tomorrow, see ya. And if I'm not going to see you the next week, we'll see you when we see you. All right. 73s, everyone.
Thanks, Nathaniel. Take
73.
care.
Thank you.
Thank you all for coming.
See everybody tomorrow night. Take care.
All right.
7-3, everybody.
7-3.